things. In this one, we'll be solving a partial differential equation, namely the heat equation. So it is of this form. It is a function u of x and t, two independent variables, as you see. And this is just the function that we're solving for. Theoretically, although we won't really go into concrete solutions because that's yet far more work, we just do the most general ones. So the idea is as follows: we have u derivated partially in respect to one of the variables t1s equals some constant c, positive constant, times u double derivative in respect to x. So partial derivative in respect to t equals c, and twice partial derivative in respect to x on the other side. Of course, this can be written via the delta squared notation, but I'll just keep it in this notation because that's the simplest way. And the way we will solve this differential equation is via separation of variables. And separation of variables is very nice because what it does basically is this: u of xt, it rewrites as x of x times t of t, as follows. And that means that u sub t will be basically, you know, that the function is written as a function, as a single variable function of x times a single variable function of t. For such functions like this one, it works. U sub t, so the left side of the equation will therefore be equalized or made equal to x of x is unchanged, and the t part gets derivative once. That's the idea. And then u sub xx will basically be derivated twice, this x part. So x of x will be a double prime, and t of t will be left as it is. Alright, so this is the main part, and now I can plug it into this equation. So what I know is the u sub t, uxx, and I can just put it here. X of x, like this, equals, so the entire thing, x of x, t prime of t, equals c x double prime of x t of t, as follows. And now I can solve in order to separate the variables. So I want to get on two sides all the functions that include x, so all the things in terms of x and all the things in terms of t to the other side. That's why it's called separation of variables. I will choose to keep the derivative things on top. That means I'll divide both sides by x of x and divide both sides by t of t. That will give me t prime, maybe write a little below for more legible, right? T prime of t over t of t equals cx double prime of x over x of x. And now that I separated, there's this idea that when everything is in terms of t on the one side and in terms of x on the other side, of course, there's this constant c. It doesn't matter if one takes it down here or it leaves it here. Prefer now maybe just choose randomly to keep it here. Then if it's separated as follows, that all things in respect to t on one side, all things in respect to the other variable on the other side, in such case what I can do is I can set both sides equal to a. I could put equals a equals this thing. That means that if this is equal to this and this is equal to a, then this is equal to the same constant a as this thing is equal to the same constant a. Things in terms of different variables equal to each other as follows will both be equal to the same constant. And therefore this lets me create new ordinary differential equations. So namely what I can do is bring this idea to the right side here, and I can do two equations which of course will have more variance, as you will find out in a second. The point is as follows: t prime of t, just like x over t, will equal to a, just like c x double prime of x over x of x. But first I will do the t prime of t over t of t equals a. And by algebraic manipulation, just using algebra as we're used to, t prime of t minus, and this was lowercase, it doesn't really matter, I just chose so it doesn't confuse things, it's still the same a that I need here. So minus a t of t equals 0. And now of course this a, well, I set this constant a, and it can have different values, so depending on those different values, we'll be getting different solutions for a. Now as you see, it is far easier to solve this part, because suddenly from a partial differential equation we have two ordinary differential equations, only in respect to one variable each. Of course, as I said, a can have different values, namely negative, positive, 0. Probably the easiest case is when a is 0. So when a is 0, this indirect term reduces nothing. So t of t, t prime of t is 0, and just integrating both sides, t of t will be some constant c1. So I'll be indexing these constants. It's the not same c like before in the initial equations, most basic formula we began in the very beginning, but it's the beginning of these indexed constants that I'll be using throughout the rest of this solution. So t of t, the first solution is c1. Let me call this c1 of t. Then the second option is, I'll just write this form, that a will indeed not be 0, it will be bigger than 0. In such case, we have t of t minus a of t of t, a linear ordinary differential equation, and via integrating factor. This can be solved quite nicely as well. This minus a, what it means, I'll multiply both sides by e to the minus at. And what that gives is t prime of t e to the minus at plus minus a e to the minus at. The minus is because of the minus at the a, t of t equals 0, because e to the minus t times 0 is still 0. Then this can be changed in a way that it shows that this is product rule, which is differentiated, or product of two functions which are differentiated. That's the way I rewrote it this way. By the way, a more concrete video on this very idea is a separate one from the past. But anyway, the point is that I wanted to rewrite this entire side as follows: t of t, the function we're looking for, times e to the at prime, and equals 0 on the other side. Then, what this means is I can integrate both sides. And again, just to check which constants we were using most recently. Oh, okay, it turns out we've only used C1 index so far. So I can use, let's say, C, we're doing both sides in respect to T, of course, just to cancel out with this prime above this parenthesis. So this entire product, before any integration by parts reason would come about, or any product rule or anything, it is actually cancelled by this integration sign. And on the right side, this creates a constant. Because we used C1, I'll use C2 now. So C2 here, T of T times e to the minus at, right here. Then t of t, therefore, will be equal to c2 e to the at, as follows. So t of t is c2 e to the at. So let's call this the second solution for t sub 2 of t. And then the third one, maybe the least nice one, but still a necessary one to consider, is when a is namely smaller than 0. So what I'll say, let's say I'll say that a is, I will say it's minus k squared, just to really emphasize that it is negative, so that this minus sign here actually changes into a plus 1. So t prime of t, a is minus k squared plus k squared t of t. I'm not gonna go that deep into this part of the solution. The point is here, via actually this can still be solved quite simply. So it's a matter of integrating factor actually as well in this case. So e to the k squared t on both sides. So t prime of t e to the k squared t plus k squared e to the k squared t, t of t equals 0. We're for new chalk. So this ends up being rewritable as t of t e to the k squared t as follows. All of them differentiated as follows, equals 0. We've used C2 as the biggest index so far, integrating both sides in respect to t again. Then we get t of t e to the k squared t equals C2, so C3 this time, and t of t therefore will equal, namely t of t is C3, some constant C3 times e to the minus k squared t. Alright, so this minus exponent right here. So this is the third solution for t. So now we've got the three solutions for t, and the entire idea of this entire process is to get these solutions for both t and x. So now we'll do for x, and after all of that is done, just to kind of show in advance what will be the eventual thing, it's basically the idea that I've shown right in the beginning, is this very idea of u of x t equals x of x t of t. Of course, one can go far deeper with Fourier series and continue and do more specific solutions, initial conditions, and so on, but now we're doing the most general possible solution. Solution that can be delivered through these basic ways. And so the very final idea is that basically you'll substitute all these variants we calculated for both t and x. So far we've done for t, now we'll do for x as well. Alright, so the next step here is to do for x, and the point is we have this cx double prime of x over x of x. So cx double prime of x over x of x also equaling this a. Alright? Cx double prime of x also equaling this a. Now again, one equation the same way. Cx double prime of x minus a x of x. I'm playing the game with the c, just leaving it there as it is. And now, for the first case, again, I can say that if a is 0, then what we only are left with is this cx double prime of x equaling 0. I think we've used c3 as the biggest index so far. Now it's safe to use c4, c5. So basically dividing both sides by the c, all that's left is cx double prime of x, still in the variable ordinary differential equation. And what this will give is x of x is this linear equation c4x plus c5. Alright, so let me call this x1 as the first found out solution for x. Alright, the next one will be cx double prime of x, again, minus using this x of x a in front here. Great, equals 0, and a will be above 0 in this case. So this stays negative. This is meant that this a here meant to be positive in this case. There's more cases to be considered. All right. So now what we will do. This is C here. All right. So now what we can do is maybe divide both sides by C. Equals 0. Now we can use this expectation that x of x is supposed to be equal to e to the rt, and then using this idea which I also discussed in a far previous video, which you can also watch, is basically r squared will happen here, e to the rt minus ac e to the rt equaling 0, cancelling out e to the rt on both sides of this equation. All that is left is r squared equals a over c, and r is plus minus the square root of a over c, where this is expected to be positive inside the square root, no complex things. All right, and thanks to this r, this produces another solution, because the expected solution was then this exponential e to the rt. That means that the x2 of x, the second solution for x, will be the biggest was, so now it's c6. C6 e to the positive a over c times x plus c7 e to the negative square root of a over c times x, as follows. And now the last solution for x of x, when a is under 0, so a is below 0, then again using this equation. But in this case, when a is under 0, I will say a is again minus k squared. Alright, so it will be this. Plus will change from the minus. I'm replacing a by minus k squared, just to denote that really is negative by all means. And now what's gotten from here, of course, this c is set to be positive throughout all the way, even if I divide it here. Alright. Like this. Now again, there's more ideas. One can see this straight away from experience, or one can simply first look at what this will do with the usual e to the rt expected solution. The expected this simplified way of looking at it. So this expected solution x of x is e to the rt. What it will give is r squared, just like was here, r squared e to the rt plus k squared over c times e to the rt, like this. Again, cancel out e to the rt on both sides. R squared equals minus k squared over c. And of course, this side is definitely negative. This is positive, so this entire thing is negative. That means that if one takes this r, it ends up being this I, or one can say plus minus square root of k squared over c I. Another way to look at it is to simply take this k and c, their square root. That means square root of k over square root of c, and put it as the multiplier inside the argument of sine and cosine, the classical solution for such ordinary differential equation. That means x of x, and again, this might get discussed in a different video. This is not the main point, just to quickly show the solution. Before we had C7, now this last solution for x of x for this I inside the, because the expected solution is e to the rt, that means we would get e to the something times I, and that's a complex number, and therefore we'll write it as cosine and sine. So we'll use C8 cosine, and there's a proof for why this turned out to be so, but I won't go into it, not much space left. Anyway, this turns out to be C8 cosine of this k over square root of c, the independent times the x, which is the independent variable, plus another constant c9, another arbitrary one, times sine without the I. Of course, this reminds you of complex numbers and the polar form, you know, going from the exponential form to this polar form. But again, the same multiplier here, k over square root of c. Just what ended up being this right side of the e to the rt equation we would have had if we left it at the e to the exponential form of complex number, k over square root of c times x here as well. Alright, so this is the third solution for x. Alright, so to go all over all of this that we've done so far, it's been many equations. The main point is we had this big equation and made it separated by setting q of xt equal to x of x times t of t. Then using the idea that if one derivates u in respect to t, that means just the t power gets derivated. If one derivates in respect to x twice, it means just the x part gets derivated twice. And so we got slowly solutions for different values for this a, that both separated sides. We separated the equation afterwards, thanks to these separate functions only x and only t, into side only in t, only in x, with this c here, which makes it not visually appealing, but anyway, it's all equal to a. And then we got this thing that this is equal to a, as well as the t variant is equal to a. On this board we have the x variant. We've done when a is equal to 0, when a is below 0, and a is above 0. All of those cases have been considered. Alright, so we have x1, x2, and x3 right here, all the options. Also before had been done this thing, that means t prime, this was just the case with the first derivative, linear ordinary differential equation, again transform. T1 ended up being just some constant, T2 ended up being c, some other constant times e to the at, T3 to also have this subscript is some other constant times e to the minus k squared t. All very much depends on all the constants that are used, their names, how one considers it, how one decides to work with all of them. All right. But anyway, to just complete all of this, what we can now do is you can do this yourself. I won't do it because it's already been a long calculation, a long time, and there's not much space left to do all of this. But anyway, the point is we are still working with this very thing. So what one can do is pick those values. So there's 3 solutions for x, 3 solutions for t. Pick one for x, pick one for t, and put them together into this, and verify if one puts this together as a multiple. So one multiplies the x solution times the t solution. That is the solution for the u that equals the u of xt that we're looking for. And one can input it back and see, verify if that works.